have the lecture on the YouTube. So actually, you don't have to really come to this class. Just take a look at the YouTube and you can get everything. Anyway, this is the content of this lecture. And we just make a review in chapter 1. Let me see. No. Let me try to. And electrical properties in non-equilibrium and characteristic of semiconductors and planar technology. Up to here, we just a review of what we have learned in the undergraduate course, right? And the second chapter, we start with the junction properties, p-n junctions basically, and the next chapter is going to be the operation principles of MOS transistor, and then bipolar transistor, and then finally we're going to cover, if we have a time, other transistors like JFET, MESFET, and SOI, and finally the TFTs. Gallium arsenide transistors and TFTs, a thin film transistor. Okay, that is the content of this lecture. And today is the first class, and we're going to talk about the review and the electrical properties in equilibrium in semiconductors. All right. Some of them are written in Korean, but I really don't have a time to translate everything into English. But next year, probably, we're going to have a textbook, everything written in English, but not this time. Okay, let's, what should I do? Let's cut off this. 희재, 이거 좀 끄고 칠판에다 내 쓸게. How can you turn it off? 저 위에 적을 거야 되는 거 아니네? 거울로 이거? Okay. As you may know, we have many statistics using for the electrical properties of materials. The typical one is the Boltzmann statistics, and Bose-Einstein statistics. That is related to the phonons, right? And for electrons and holes, we have a Fermi-Dirac statistics. Okay, that is for electrons and holes. And the Boltzmann is basically is applied for the particles, right? So this is the most popular one, Boltzmann, and the most simple. It's just written as N is equal to available potentials times e to the minus e star over kT. Okay, this is a thermally activated process, and E star is going to be called activation energy. activation energy. Yeah. Okay. So what it says is basically the available sites, and if it can have the activation energy thermally overcome the barriers, then the successful particles is going to be written as this exponentials. This is statistics. That's what the Boltzmann statistics is about. Okay. So when you take a log of this, log n is equal to log n minus E star over k, and then 1 over t. So the beauty of this Boltzmann statistics is that when you plot that in the 1 over t, this is a high temperature, and of course this is a low temperature, then we're supposed to have a straight line. Okay, and the straight line, the slope is related to the activation energy of this system, and if we come to understand the activation energy, then we probably can get a clue, the basic mechanism of that reaction. That's all this Boltzmann statistics is about. Okay. Now, if we have to use the for electrons and holes, we have to use the Fermi-Dirac statistics, then life becomes very complicated. As you know, Fermi-Dirac statistics is complicated. It is a Fermi energies and the probability 1/2 at the Fermi energy levels. And that Fermi energy is related to the electrochemical potential of the system, such and such and such. So it would have been very complicated if we talk about the conduction of the materials, because we have to use the Fermi-Dirac statistics for the electrons on the conduction band, which is actually contributes to the conductivity of the materials. But fortunately, the electrons and holes which can contribute to the conductivity of the system, that is some few kT energies over the conduction band, so that the statistics is related to the tail of Fermi-Dirac, and the tail of the Fermi-Dirac statistics is the same to the tail of the Boltzmann statistics. So in Fermi-Dirac statistics, you should say at the Fermi energies something like this. This is probability 1/2, something like that. Okay, if you plot this, the probability, and we call this as a Fermi energy, something like that. Okay, so this tail region where the energies of electrons are few kT over the energy of Fermi-Dirac, the Boltzmann statistics comes close to this, so that the Boltzmann statistics is equivalent to the Bose-Einstein at these tail regions, and the electrons which contributes to the conductivity of the materials have the energies corresponding to this tail region of the statistics. So what we can say is that the electrons in the conduction band can be said some of the effective, we call this effective density of conduction band. That is some of the, that is equivalent to the potential of the reaction can occur. And then we just use the Boltzmann statistics, and here at this time the activation energy is the energy corresponding to the gap between the conduction band and the Fermi energies. So what it says is that if you have conduction band and the valence band and the Fermi energies of this system, then the electrons which contribute to the conductivity of the materials are the electrons sitting at this conduction band, above the conduction band. And these particles, if you like, the electrons, should have the activation energy corresponding to this much, right? So if you want to say the particles successfully overcome the energy barriers corresponding to this gap, should be called the conducting electrons. Okay, that is the free electrons. So this N is really contributes to the conductivity of the materials. Say the conductivity is going to be N, Q, mu, the mobility of the materials. Okay, so this N is electrons sitting at the conduction band, and those electrons can be represented by the Boltzmann statistics. Okay, and at this time we can say this is the effective density of states of conduction band. You can tell the same story about the holes. So we can deduce the equation corresponding to the number of holes, okay, is equal to the effective density of conduction valence band in this time, okay, and then e to the minus e star over kt, and here again the e star is going to be ef minus ev, valence band, the distance between the Fermi energy and in the valence band. Okay, that is the equilibrium concentration of the electrons and holes. And the important thing to notice here is that the P-N product, in any case, the P-N product is going to be Ni squared, the intrinsic concentration of the free carriers. This, if the material is in equilibrium, this holds. Okay. If it is not in equilibrium, even though it is in under steady state, the P-N product is going to be greater than Ni square or less than Ni square, depending on the situation. That is the non-equilibrium situation. But as far as the semiconductor is in equilibrium state, then the P-N product, electrons and holes product, should be equivalent, equal to the intrinsic carrier concentration square. That is the definition of the equilibrium in semiconductors. Okay? So from here, you can see that in a P-type semiconductor or N-type semiconductor, N-type or P-type, depending on the doping, we can set is a P-type or N-type. Okay, N-type semiconductor, what you can say, the N is equal to the doping density. Okay, we are going to dope. If you dope the semiconductor, it means that you are going to mix foreign atoms, dopant, say, much more than the number of free carriers you can have. So in N-type, we should say we put a large number of electrons so that the electrons in that material is going to be equivalent to the number of dopant atoms that you put artificially, intentionally. Then we can say the minority carriers, P can be said as Ni squared over Nd. That's simple. Okay, if it is a p-type, of course the p is going to be the number of acceptors, and then the minority carrier electrons in p-type materials can be said simply just like this. So in the semiconductors, the important parameters now is going to be the effective density of states of conduction band, the effective density of states in the valence band, and band gap, and the intrinsic carriers it can have. So what is a typical semiconductors? I think this table summarizes everything currently known as important semiconductors, like silicon. It's in the text. Okay, germanium and gallium arsenide. I should write in the order of invention. Like first we have germanium. That is the first ever known as a semiconductor in 1949, right? And then silicon. Okay. And the effective density of states conduction band, that is in the order of 10 to the 19th and 2.8 times 10 to the 19th. But in gallium arsenide, which is famous in the space, that is a 4.7 times 10 to the 17th only. So gallium arsenide is not a good semiconductor. Okay, and about the NV effective density of states is almost the same to the conduction band, but say 10 to the 19th, and this is a 7.0 times 10 to the 18th. What about the band gap? Band gap is 0.68. It's so small. So it is not stable. That's why every industry moved to the silicon instead of germanium, the first inventions. Okay, the band gap is small, which means it is not stable. It is very sensitive to the temperature, for example. Okay, and gallium arsenide has large band gap, relatively larger band gap than the silicon and germanium, so that it is very immune to the cosmic rays, very strong rays in the space. Okay, that's why the gallium arsenide is used in the space. Now, intrinsic carrier concentration 2.5 times 10 to the 13. For the germanium, because the band gap is small, so that the intrinsic carrier concentration is relatively large. And this is the 1.5 times the 10 to the 10th. Now, in gallium arsenide, just have 10 to the 7th. Okay? So, currently, this is the most important in the industry. And this is very important in space. Okay? And this is not stable. Sensitive to the environment. So, even though the germanium is the first invention as a semiconductor in 1949, nobody is using the germanium as a semiconductors these days. Okay, secondly, I want to talk about the Einstein relations. I better erase this thing. I hope you guys are familiar with this kind of content, right? This materials has been covered in your undergrad courses, right? Einstein relations. Basically, it is related to the diffusion coefficient and the mobilities. We want to know the relationship between the diffusion coefficient and the mobilities. Why are we interested in these parameters? Diffusion coefficient, what it says, the flux is going to be concentration gradient is related to the flux of moving particles in this fashion. So if you plot, okay, the flux of moving particles and concentration gradient, again, we're going to have a straight line. And that slope is related to the diffusion coefficient of the material. And that is the material constant. It's amazing, isn't it? It's really amazing. Now, about the mobilities, if you want to plot the velocity of the particles and then the electric field, then you can have the straight line, and that slope is mobility, and that is a material constant. So this is the material constant, and this is the material constant. Those are related to the moving flux of the particles, okay? And this diffusion coefficient is related to the concentration gradient, but this movement of particles is related to the electric field. What is field? Field, a force in a distance. There's a very important thing. Force in a distance. That is going to be called the field. Okay? So, Einstein thought there should be a relation between these two. Okay? And that is basic properties of semiconducting materials, especially when it makes junctions. Okay, concentration gradient of the particles. Now let's see. We just talk about the one direction flux. Then that is going to be set in terms of the velocity of the particles like this. And then this velocity is related to the electric field in these fashions. Right? And at equilibrium, the drift flux is going to should be equal to the diffusion flux. Otherwise, there is accumulation, okay, or depletion of the particles, which is not in equilibrium. Now, NQ mu EX should be concentration gradient related thing. That is a fixed first law, by the way. Fixed first law. And we know the concentration can be represented by EI over EF over KT. You can notice that this is a little bit different from the Boltzmann statistics that we have talked earlier. We said e to the EC minus EF over KT. Okay? Those two equations exactly the same equation, because at this time the potential of the electrons to be excited to the conduction band is relatively from the conduction band. So that's why we can take the activation energy from the conduction band. But if you say intrinsic carrier as a potential particles to be excited to the conduction band, then only thing you have to do is just changing the conduction band energy into the intrinsic energies. Right? So these two equations are exactly the same equation in terms of the Boltzmann statistics. Okay, so here if you make a first derivative with respect to the x, then you can have ANI e to the minus EF over KT round x over round e to the EI over KT. Okay, so EI over KT mu EX equal to D round x over round e to the EI over KT. And now, since the electric field is a first derivative of the potentials, and that is intrinsic energy slope with respect to the physical space. Okay, so we can say KT mu 1 over Q round EI over EX is going to be KT over 1 over E to the EI over KT round x round EI. Okay, and then you can eliminate some of the equations here, the left hand side and right hand side of the equation. Then we end up with the Einstein relations, which is going to be QD is going to be KT mu. That is the Einstein relations. So simple. If you multiply the diffusion coefficient with the charges of each particle has, it's going to be, the KT is what? Thermal energies. Okay? This K is a Boltzmann constant. Boltzmann is amazing constant. If you have a temperature like, what is the room temperature in terms of the absolute temperature? 300 K, right? And if you want to know what energy is corresponding to, all you have to do is just to multiply this with the K, Boltzmann constant. Then you end up with 0.25 electron volts. So you can convert the temperature into the electric voltage, the energies, simply by multiplying the temperature with the Boltzmann constant. This Boltzmann constant is that amazing constant. Now, this KT is the thermal energy. We just call that as the thermal energy, okay? And if you multiply the mobility of the materials with the thermal energies, and then you can convert that into the diffusion coefficient any time. So let's say, in metallurgies, you don't have any electrical field because there are so many free electrons. You cannot have electric field internally inside the metals. Everywhere it's the same, right? And you have particles only moved by concentration gradient in the metals. Okay? Then you can have some diffusion coefficients there. Now, if you have some diffusion coefficient in some certain specific metals, you can convert to the electron mobilities with Einstein equations, even though you are not actually having any mobilities inside the metals, because you cannot have the electric field inside. So this is a very important and useful relations. So that is the basis for the junctions. Later we're going to talk about this later. Well, for now, let's just move to another topic, which is going to be called the quasi Fermi levels. What is the quasi Fermi levels? The Fermi energies, it can be only defined under the equilibrium situations. If you have a non-equilibrium state, then the Fermi energy is not going to be defined. Okay? So Fermi energy is an equilibrium energy state. So what is a non-equilibrium state? If you have a junctions, for example, N, P junctions, if you shine the light on this, H by omega photons, then it suddenly becomes a non-equilibrium state, which means NP product in any section of this junction is not going to be equal to the Ni square if you shine the light. If it's in the dark, of course, it's an equilibrium state, then NP product in any section of this junctions is going to be equal to the Ni square. But if it shines a light, then the equilibrium is going to be broken. Then what's happened? It may be in a steady state, but not in equilibrium state. So this equation is not going to be equivalent to this Ni square. Or if you apply the voltages, forward bias or reverse bias, then it is not in equilibrium state anymore, which means you cannot define the Fermi energies. If you cannot define the Fermi energies, then how can you use the Boltzmann statistics to find the number of free carriers in any part of this materials? That's impossible, right? If you cannot define the Fermi energies. So people have thought about the quasi-Fermi energy levels. And to understand what it is, let me just give you the example why people have thought the quasi-Fermi energies. Okay? Let me give you an example. It's on the text. In the p-type material, let's say the accepted concentration is going to be 10 to the 16th per cube. That is very lightly doped p-type materials. And let's say the lifetime by shining the light as a 10 microsecond. And the generation rate is going to be 10 to the 18th carriers per cube sec. That's the unit. by shining light. Now, if you have these materials, then the number of electrons is going to be equilibrium concentration of the electrons before shining the light, and then the lifetime of electrons in the material, and the generation rate, simply. And then it's going to be Ni squared over Na, because it's a p-type material, and it's a minority carriers, so that the number of minority carriers in equilibrium can be driven in simple equations, right? And then 10 to the minus 5 sec, 10 to the 18th, and you end up with a 10 to 13 per cube. Right? This Ni squared over Na is a 10 to 6, somewhere around there. Because Ni is, let's say, 10 to the, what? 12. So Na is 10 to the 16. So this number is end up with 10 to the 8th something, right? And 10 to the 8th plus 10 to the 13 is going to be 10 to the 13th. Are you guys agree with me or not? Your same poker face. You guys have the same face all the time during the lecture. Now, the P is a P naught plus tau GL, and that is Ni, that is going to be 10 to the 16th. Okay? Because this is the 10 to the 16th, and this is 10 to the 13th, so that is going to be 10 to the 16th per cube. Okay? So, we know the results. When you have a p-type materials, which is doped to 10 to the 16th, and you shine a light, then it's going to be in non-equilibrium states. It may be on the steady states, but not in equilibrium. So we cannot set the Fermi energies. Because the Fermi energy, by definition, it is a kind of energies, electrochemical potential in equilibrium of the materials. But we know the number of free carriers, number of electrons and number of holes in this system. With knowing the answers, we want to define some Fermi energies which may produce these numbers applying the Boltzmann statistics. So what I'm saying is, this number of electrons, it gotta be related to some Boltzmann statistics, which is going to be NC e to the minus E star over KT, and if you put this Ni, okay, then this energy is going to be, the Fermi energy should be related to the distance from the intrinsic energy levels. And this Fermi energy is not really a Fermi energy, because it is not in equilibrium, but kind of a Fermi energies. And then we call that quasi-Fermi energies. And then we just say, put a star there. It's not really Fermi energies, but it can work as a Fermi energies to get these numbers if you apply the Boltzmann statistics. That is the Fermi energies, quasi-Fermi energies. So you can deduce from here that the quasi-Fermi energies level is going to be 0.18 electron volts above intrinsic energies. from this equation, we know this Ni. I told you there's a 10 to the 12 something somewhere, okay? And everything is known. We know EI, okay? So we just simply get these numbers, that is 0.18, and then we can set some, not Fermi energies, but corresponding to the Fermi energies with respect to the Boltzmann statistics, okay, and the distance from, this is conduction band, but the intrinsic level is somewhere here. That is EI, and the distance is 0.18 according to the calculations. And we call this level quasi-Fermi energy level. All right? We can do the same thing for the hole. And then that is EF double star, you may say, that is a 0.36 electron volts for holes. And then that means if we have a conduction band and the valence band and intrinsic carrier levels, the Fermi energies, quasi-Fermi energy levels for the holes, just for the holes, is going to be somewhere below 0.36 electron volts. You are going to have quasi-Fermi energy levels for the holes, and here you have quasi-Fermi energy levels for the electrons, and the distance is going to be 0.18 electron volts. So in non-equilibrium semiconductors, and you may see most of the semiconductor devices are working under non-equilibrium conditions. None of the semiconductors is working at equilibrium conditions. So actually these quasi-Fermi energy levels may be more important than just the equilibrium Fermi energy levels, right? And of course, if you shut down the shining light, cut off the light, then this quasi-Fermi energy level for the electron is going to be equal to the quasi-Fermi energy level for the holes, equal to the Fermi energy levels. And again, you are going to have NP product under equilibrium like this. Let me just take a pause here and then say something interesting. Okay, I just talked about quasi-Fermi energy levels. Energy levels. And before this, we have discussed about what? Effective density of states. Okay? Effective density of states of conduction band. And you may have many cases for the sometimes heard effective density or effective mass of materials, of electrons. You heard the effective mass of electrons and holes, right? That is terribly small. You cannot measure the weight of electrons with balance. is 10 to the minus 19th or something. So you cannot measure the mass, but you may heard effective mass. So what is a quasi-effective, and another term, pseudo single crystal, for example. Not single crystal, but is almost the same to the single crystal. That is a pseudo single crystal. Another term we can think is a semiconductors, let's say. What are those in English? Semiconductor, is a conductor or insulator? It's something we don't know. Sometimes it is a conducting and sometimes it's not conducting. Then we could call that a semiconductor. It's not a materials that are conducting half. You should remember that. The silicon is a semiconductor, but basically it is an insulator. Now, the only difference between the silicon and the stone is that in the silicon, you can massage it to make it conducting. But the stone, no matter what you do, you cannot convert that stone into the conducting materials. And then we call that the insulator. But the semiconductors is basically, originally, it is an insulator, but you can convert it to the conducting at your will. That's why it is called the semiconductor, not half conducting materials, right? So these things have in common. What is effective mass? We cannot measure the mass, but if you plot the force and acceleration, then you are going to have a straight line. And that slope is corresponding to what? Mass. We call that effective mass. So when you measure the weight, the mass of electrons, what you should do, you should put the electron in the field so that you can sense the force you can obtain with the electric field. Okay? That electric field is related to the acceleration, so that you're going to have a straight line. And we call that is correspond to the mass. And then we call that the effective mass. So whenever you could encounter this was quasi-effective, pseudo, semi, all you have to do is, we don't know what it is, actually. We just regard it corresponding to the density, mass, or whatever. No? So whenever you have words like this, it is not wrong to think we don't know what it is, actually. So whenever somebody says the effective mass is such and such, then you just regard it. He doesn't know anything about the mass, actually. Just regard, okay? Okay. This Wednesday we don't have a lecture because it's Chuseok. Okay, so I'll see you guys on the next Monday. Have any questions? What do you think of my English? It's too fast? It's too difficult? Why you guys have a poker face during the lecture? Sometimes you should laugh, sometimes you should be surprised at the results, sometimes you should you should show some agreements of my lectures sometimes. But you guys always look the same. What's the problem? Do you have a bad family business? What? Okay, next time, let's make this lecture more interactive, not just to make a one-side lecture. I don't like it. Okay? Okay, I'll see you on the next week then.